Okay, so I am going to talk to you about the memory behavior of OCaml programs. I also going to present you memory profiling tools that we are developing at OCaml. So why are we studying the memory behavior of OCaml? Because we want to decrease memory footprint of our OCaml application. We also want to fix some memory problems like memory leaks. And we want that our application spend less time in the memory management. So let's start with applications that use too much memory. So it's like applications with, it impacts applications with big memory usage, like assembly compilation tools, for example. I have an example here of a data representation. We have type T1 and type T2. And which type would you choose between the two types? T1. T1? T2? So of course T1 is the type that we choose because OCaml compiler is able to optimize and unbox the float in the type T1 instead of type T2 where we have two floats which is boxed. So this is a very simple example, but sometimes we cannot see this kind of things just looking at the type. So application that use too much memory can, one of the causes can be the bad data representations, or maybe we can have also the bad use of collections, and etc. So memory leaks. It's which when applications fail to free the memory they have used. We also have an example here when we add values to a collection and forgot to remove them. So we can see here in the first line that we add value x and y in the table. Then we use the function do something that may fail with the table, which succeed. So we remove the value x from the table. So back to the first line. We add the value x and y in the table. Then we do the function do something that may fail, that actually failed. So we directly go to the with statement and forgot to remove the value x from the table. It's a memory leak. It's kind of doing a malloc without the free in C. Cost of memory management is when our applications spend too much time in memory management. When we look at the example here, we actually expect that the program run a little faster, but it's behave differently than we expected. So we can see here a for loop that just multiplies the value x by 1, and when I compile and execute it without the multiply 1 at the end of the loop, I get 1.8 seconds, and when I forgot to add the multiply 1, I get 3.6 seconds. So actually I was expected without adding the multiply 1 at the end that values were unboxed in the for loop, but actually it was boxed. It was boxed in the for. The value x was boxed in the for loop. So by adding the multiply 1, the compiler can see that there is no need to box the value x. So we need some tools to understand when and why memory is allocated. So consequences of these problems is in best case it just slows the application. GC can spend some time to trying to free memory in the heap. In the worst case, it just runs out of memory and crash. So what kinds of tools we are developing to help to understand the memory usage? I will present you 4 tools that we are developing. First, the Allocation Profiler, Region Inference, Snapshot Memory Profiler, and Continuous Memory Profiler. So, allocation profiling. Our tools profile where application allocates memory, It was originally inspired by the Bozman method, which record information on the stack state periodically after some allocations event. It displays the allocation hotspot and generate an approximated call graph, which is weighted by the number of bytes allocated. We just need to link with a modified runtime, which will allow us to save backtraces at sampling points, and just set a sampling rate, and it's ready to go. So let's do a demo. So I just first link OCaml with the modified runtime. Then I configure the sampling rates by exporting the OCaml run param values, n equal 4k. Then I run my program to save backtraces in a main.out file. Then I generate a JSON file with OCaml prof to get my nice graph that we have here. Ta-da! So, what is all of these colors and what represents the graph? So one circle represents 100% of the allocation. We can see on the bottom of the graph that we have the typing module, which takes around 40% of the allocations. We can see on the top that parsing phase don't allocate so much. And when we have the graph, we can mouse over and see all the details like the allocations memory. We can also click in the module and go inside the module and see all the details. And it's already on our website if you are interested.
Question?
Yep.
Could you do essentially the same kind of stuff with, instead of using modified runtime, using proof? The point is, look, you have these tools, you use kernel counters for keeping what's going on, and you can get stack traces. Yeah. Which I think, and I think you can more or less tell perf, like, whenever this function is called, I want an event. So it seems like you should be able to do it without any extra instrumentation and get more or less the same data.
So maybe we can do that, yeah.
Another question. So what is it that you are counting exactly?
Sorry?
What are you counting?
The memory that was allocated.
Each allocation counts one? All right. And this goes both in minor heap, major heap, C primitives, everywhere.
Yeah.
Okay. And last question. So you should have modified the runtime system, but you also need a modified OCaml compiler to do this and so on.
To do this, no.
The allocation in the minor heap is in line.
So actually, you force a minor collection by putting a limit, like you do for the signals.
Okay.
You just set the limit to the size of the sample, so that it will trigger a minor collection, and then you don't do a minor collection.
Okay. Thank you. I'll show that.
Then we built a tool based on region inference by Toft and Talpan that approximates the values lifetime of our program. Basically, it's every value is assigned to a region, which is kind of lexical scope. We then generate an annotations file, a file that contains annotations that help us to track values that we don't want in a region. So I'm going to show you an example. We built a plugin in Emacs that allows to show us, to highlight every value in a region. So we have the same program on the left and on the right. I ask Emacs to show me all values in the same region with table 1. And actually I was surprised that every value was in yellow. So that means that every value is in the same region. And then we can see that I made a little mistake in function f table 1. And instead of adding the values in table 1, I added in the table 2. When I correct this little mistake, I re-ask Emacs to show me the region, and then we can see that all values in table 1 is in yellow, and all values in table 2 are in blue. So as values does not interact between each other, it's quite expected behavior instead of the one in the left. So we then have snapshot profiling, which is a work in progress, which gives us detailed liveness information. For now, we have a depth of the memory graph, and we want to recover more precisely types and root name information to know what types and values each all the memory of our applications. We already get some nice graphic here. On the right, you can get the types in the heap, in the memory, and we take snapshot after each garbage collected and concatenate it to obtain this graph. Now we have to work on is it the expected behavior, or is it or something go wrong in this graph. That's the work we are working on. Finally, continuous profiling. It's also a work in progress. It will give us the global memory behavior of our applications. For now, we log all allocation and garbage collection events in a file, and now we want to extract useful things and information from the raw data that we have to try to build some displays tool to show us to the users. To conclude, I present you the four tools that we are building at OCaml. We have Allocation Profiler, which shows us the allocation hotspots, region inference that explains the values interaction, Snapshot Memory Profiler, which gives us the data liveness information, and the continuous profiler that will give us a global memory behavior. So the future works is to have more and more display tools and try to recover more precise types in the snapshot profiling, and maybe recover memory block lifetimes with the continuous profiling, and maybe you get some ideas that we can talk about. Thanks.